so far in this mini course I've been like working building like with small lemmas I was trying to build up, but now I'm sort of running out of time. So I will do the opposite. I will do what's called the top-down. So I will just state one of the most celebrated theorems in Kähler geometry, and I will try to explain it as much as I can in the hour I have. So there is this theorem. It's Yao, 1978. The theorem is as follows. Let's say that M omega is a compact Kähler manifold. With first Young class C1 of M equal to 0. Then there exists a unique what's called Kähler metric, so omega Cy. So this is a Kähler metric. Such that first is the RAM cohomology class. So this is the cohomology class of omega Cy is in the class of omega. The background measure we started with is an omega, so this is an element in the RAM cohomology group of the manifold. And the crucial thing, and here comes the main part of the theorem, is that the Ricci curvature is 0. Ricci curvature of omega Cy is equal to 0. So that's the key. Yeah.
What is C1M?
What is what?
C1M.
I will explain. Yeah. I will.
A second question. So this might be another stupid question. So M omega, is that enough to give you like a Kähler structure?
Yeah. Let me explain here. So M is a compact complex manifold, as we've been saying, and I have a Kähler metric G, but because I have this complex manifold in the background, this metric G defines this omega, the fundamental form, the symplectic form of the metric. So omega is the fundamental form of the Kähler metric. So thanks. So the plan for this hour is to explain as much as I can of how to read this theorem. But first, before giving all these explanations, I want to put this theorem into perspective. Why is this such an important theorem? Well, here the conclusion is here is this conclusion with the Ricci curvature. To put this into perspective, before this theorem, the only examples of Riemannian manifolds, compact Riemannian manifolds with vanishing Ricci curvature were flat tori, which is kind of trivially flat spaces. So this theorem produces the first non-flat compact Riemannian manifolds, Ricci flat compact manifolds. And moreover, up to this day, this is basically all we know of compact Ricci flat Riemannian manifolds. These are basically all the examples, apart from exceptions in real dimensions 7 and 8. There is something called the G2 spin 7, some special non-metrics, but apart from these exceptions, which are kind of related to Kähler because the constructions also use Kähler geometry, this is just the only source we know of these compact Riemannian manifolds with vanishing Ricci curvature, which are not flat. So now, let's explain first what is this C1. C1 is what's called the first chain class. So first chain class. So this is C1M. So if M has a complex dimension 1, so if M is a Riemann surface, then dimension is 1, then this is the Euler characteristic. Then this C1 of M is just the usual notation is chi, is the Euler characteristic. So I want to be just a little bit more precise. So C1, the definition of C1 is an element in some cohomology group. So this is an element in the second cohomology group of the manifold with integer coefficients. If this is a two-dimensional surface, real two-dimensional, this is canonically identified with the integers by integration or the manifold. So then, this is the familiar thing that we basic, the most basic, one of the most basic topological invariant. So here C1 of the two sphere is 2, C1 of the torus is 0, and C1 of a surface of genus 2 or more is negative. So now what about higher dimensions? So in higher dimensions, the definition is sort of complicated, so I'll just give sort of a sketch what is this about. So what is this about? So what are Chern classes about? Chern classes are sort of topological invariants of vector bundles. So you know, vector spaces you can just classify by dimension, finite dimensional vector spaces. Yeah.
Sorry, does that say minus C1 is 2 under the sphere there?
This is not a minus. Yeah. Well, I think this was written. C1 of the sphere is 2. C1. The other characteristic of the sphere is 2. Yeah. So what I was saying is that Chern classes, we use Chern classes to study like vector bundles. Yeah. So vector bundles are like sort of vector spaces parameterized with the base manifold, parameterized the manifold. But then the thing is that these fibers of the vector bundles, vector spaces, in general, they can sort of twist as you move them in the base. So the most basic example is a Möbius band. So a Möbius band is a rank 1 real vector bundle over the circle, but as you move along the circle, the real fiber twists around and it's not a trivial vector bundle. So a Möbius band is not a cylinder. A cylinder is a trivial vector bundle over the circle. The Möbius band is not. Chern classes allow us to distinguish when a vector bundle is trivial for complex vector bundles, when the fiber is a complex vector space. So the key thing that we will use is that if L, let's say, is line bundle, C line bundle, so the fiber is a complex numbers line bundle over a manifold M, then C1 of L is 0 if and only if this bundle L is trivial. So it's in some sense like a cylinder. So what I mean trivial is that I have a smooth section IE. In this particular case, when the fiber is only one dimensional, being trivial means that we have a trivializing a trivializing smooth section, let's say here. So IE, there exists, if we have this is the projection map, because it's a bundle, we have a section, an inverse that is nowhere vanishing. So smooth. So as this is smooth section, never vanishing. So that's the only thing I want to say about the chain classes. Somehow allows you to distinguish when you have a trivial vector bundle or a trivial line bundle in our case. And then what are examples of complex manifolds that satisfy this property? So well, first, this is the germ for a line bundle. Now, what is the line bundle that we consider? In our case, we consider the line bundle L. On a complex manifold, there is something called the canonical bundle. So you always have, whenever you have a manifold, you always have some bundles that come always with a manifold, like tangent bundle. You have a manifold, very nice. You have tangent bundle, always comes with a tangent bundle. And then you can also call tangent bundle, the dual. And then in complex geometry, there is this thing called canonical bundle. So it's a line bundle, it's called a holomorphic line bundle over the complex manifold, whose sections are holomorphic and zero forms. So that's called a canonical bundle in algebraic geometry. It's a very important object in algebraic geometry. And that's the line bundle that you need to consider to define what is C1 of M. So this actually was called the anti-canonical line bundle. So what is this? Is just if you have this 1-0 tangent bundle that I define, and it's the top x0 power of this 1-0. So in local coordinates, so these things in local coordinates, this at 1 after this at n, this is a trivializing section of the canonical. So this is section of the canonical line bundle, what's called K of M. But anti-canonical is dual, so it will be like wedge products of multi-vector fields or something like that. But anyways, when you consider this particular line bundle, that's what gives you the first in class. So our definition, C1 of M, is C1 of M is by definition the first in class of this line bundle. So the anti-canonical line bundle. That's the definition. And so for our purposes, again, we're very interested in the case of this theorem, C1 equals to 0, C1 of M equals 0. So this there is a subtlety here, but almost equivalent to say that there exists a holomorphic volume form. Almost equivalent to saying that there exists M0 form on M, which is holomorphic. So what it is just a section of the bundle of M0 forms. So it's a holomorphic section that in local coordinates it just looks like this, maybe up to some multiple here with this F narrow 0, and holomorphic. So that's what we will need for understanding this theorem. So examples. What are examples of complex manifolds with 0 first in class? So let's do, I will do the example of a hypersurface that we discussed. So we have considered the manifold hypersurface in projective space. So M is the zero set of a homogeneous polynomial in CPN. And so this homogeneous polynomial, let me just be concrete. I will just take the following polynomial, Z0 power D plus Z1 power D plus Zn power D. So this, the zero set of this in CPN is actually a smooth complex manifold. And then the first in class of this manifold one can calculate by something called, in algebra geometry, this is called the adjunction formula. But anyways, there are tools from algebra geometry that allows us to calculate these chain classes. And in this case, it is n plus 1. So let's take n, the dimension of n, minus d, the degree of polynomial. But as I said, this is an element on the cohomology group. So I need to, so this is just a number, so I need to multiply this by some element in the second cohomology. I will explain this now what it is. H here is an element in H2 of CPN set, which has and this H is what's called the hyperplane class. This is the Poincaré dual of hyperplane, complex hyperplane in CPN. But let's not worry about this. The formula tells us exactly for which degree this thing is 0. So all that matters is that this is something that's non-zero, and this vanishes precisely when d is n plus 1. So for this hypersurface M, so M is a complex manifold of dimension n minus 1, and this C1 of M is 0. Is 0 if only if the degree of this polynomial is n plus 1. So, example, if this M, let's say CP2, so in this case I'm taking the case n equals 2, and M is in CP2, so then D has to be equal to 3, and M is what's called the elliptic curve that we discussed, elliptic curve, so it's just a torus inside CP2. In this case, of course, this case of the dimension of M complex dimension 1 elliptic curve, they have this flat matrix, and it's not the. So the first really interesting case where this theorem applies is where let's say n is equal to 3, so we have m in CP3, and the degree d has to be 1 more than n, so it's 4, and m now is a complex surface, complex dimension 2, so in this case m is what's called a K3 surface, and these convex surfaces, they do admit by this theorem this Ricci flat matrix. So this is the first interesting. Yeah.
For this particular class of examples that you wrote down, is this an if and only if statement, or are there examples?
Oh, yeah. I didn't say that, but this is always true. Whenever you have a Kähler metric with vanishing Ricci curvature, the first in class has to be equal to 0. That I didn't say, but it follows somehow from Chern-Weil theory. Ricci curvature, the cohomology class of the Ricci curvature is a representative of this cohomology class. So Ricci curvature is a representative of this cohomology class. So if it's 0, this cohomology. So it's an if and only if, yeah. So okay. So any other questions?
We have one.
Yeah.
I'm familiar with Chern class, but usually it's the Chern class of the tangent.
That's right. So C1 of a manifold, you want to define it as C1 of the tangent bundle of a manifold.
Mm-hmm.
But what is C1 of a vector bundle? You take the top exterior power of the vector bundle. That's what you do. And that's what you get in this case. Yeah. So, okay. So, come back, C1 equals 0. So now I want to explain what is a little bit about the Ricci curvature in Kähler geometry. So what is what I want to get at? So what I want to explain is that how we can write down this condition. The thing of Kähler that makes this makes it possible to prove such a thing is that this equation in Riemannian geometry, this is an equation of a tensor, a really complicated thing. In Kähler, this will reduce to a scalar equation. This will reduce to an equation for a function. And that's thanks to some extra properties that Ricci curvature of Kähler manifolds have, which is basically how the Ricci curvature relates to the volume form of the manifold. So let's explain the Ricci curvature. Ricci. So, well, I just recall Ricci curvature is a concept of Riemannian geometry. You have a Riemannian manifold, you can define what's Ricci curvature. The Ricci tensor is a tensor of the same type as the metric. It's a symmetric 2-0 tensor. And then, because it's a symmetric tensor, you can just specify the tensor by saying what is the value of the tensor when you evaluate the same vector. Like Ricci of xx, that determines what is Ricci of xy, because it's symmetric. So then, what is Ricci of xx? So we can normalize and say that x is a unitary vector, or unit vector, and Ricci of the unit vector is just you add all of the sectional curvatures for all planes which have that vector. Well, you take an orthonormal basis with that vector, and then you add all the sectional curvatures of the plane that contain that vector. So the Ricci, for example, of the n-dimensional sphere. What is Ricci of n-dimensional sphere? Well, I take an orthonormal basis, and then I need to add the sectional curvature of all the planes that contain a given vector. Well, and there are n-1 of such planes. So the Ricci curvature of the n-dimensional sphere is n-1. And being Ricci flat is this wonderful property that you just take any vector and you add all the sectional curvatures and you just get 0. So the curvature, the manifold curves, take positively and negatively in such a way that it's balanced, like at every point in every direction. So it's such an incredible condition. So now, but now how we describe this tensor with formulas. So now, in the case of Kähler metrics, this Kähler metric has in complex coordinates. You can write down this Kähler metric as some Hermitian. So this is a Hermitian matrix. So it's a function. These are functions, and they all together they make a Hermitian matrix at any point. And the thing of Kähler, the Kähler condition tells us that we can choose these coordinates to be holomorphic and normal. So we can choose these coordinates such that this metric tensor osculates the Euclidean. So this is the Euclidean tensor up to second order. So, and then we have second order terms. So, and this second order terms is precisely what's the Riemann curvature. So this is K, L. So I will start using like the standard Einstein convention. So that's and this is the Riemann curvature. Plus some higher order terms. So now Ricci curvature, it relates to volume. So now the Ricci curvature appears when we calculate what's called the determinant. Well, we can calculate the determinant of G. So by G here, I just mean G is just the matrix, but so this is an n by n matrix of functions. So this Hermitian metric, and then the determinant, well, the determinant. This is close to the identity. The determinant is the trace. Is the relative determinant, but the identity is just the trace. So the determinant of G. So this is basically 1 minus, and then you need to take the trace. But then when you get the trace, that's where you get this Ricci curvature, because when you take the trace, you have I, bar, J, K, oops.
Sorry, what do you mean by when you write the bar over an index?
Yeah, this, I'll explain. So, I will explain here. So, the metric G, I, J bar is the definition of metric G on the vector set I and set J bar. And then if we are with curvature, I think, well, one can define curvature with this formula, but in general, if I R, J, K, L bar, this is the Riemannian curvature on these vectors. Well, I, J bar, K, L bar. That's so in the last lecture I started doing these calculations because I said in practice we work with these complex vectors. These are complex vectors, and we extend the metric G and Riemann curvature in a way which is complex linear in all of its arguments, and we define this context here. So here, well, here I include the sum because I am not respecting the convention here, but it's okay. set bar L, and now, but this is precisely Ricci curvature. So determinant of G is just 1 minus Ricci curvature K L bar, so K so bar L plus higher order terms. So, and here it might seem weird why it's like no bar bar, no bar bar, but again the Kähler metric satisfies these compatibility conditions with the complex structure that they translate into conditions on these things vanishing. So if you do ij without the bar, you get 0. That's the Hermitian condition. And then, and similarly for curvature, you might also need to use the Kähler condition. But if you here in curvature, if you have like 3 of the same type, so 3 bars or 3 bars, this component of curvature vanishes just from the compatibility conditions of being Kähler. So one used to like have 2 of each or something. And same for Ricci. But anyways, the point is that we have this, so we can recover the Ricci curvature from metric. So Ricci curvature on a Kähler metric, the Ricci J K bar. So this is what I can do. I can do the following. So I can take, let's say, log of this. So if you take log, the function log near 1 is basically the identity. The derivative of log is 1 as 1. So if you take log, you can basically forget this thing, absolute higher order terms. So then Ricci, you can just recover by taking, so this is set K, set bar L of the log of the determinant of the metric. So that's the key formula in Kähler geometry. So this is okay. There is no analog. Well, there is a form. You look at the formula remaining matrix for the Ricci tensor in local coordinates will be nice. But we have this very nice formula in Kähler geometry. So now.
So sorry, what have you used the Kähler condition?
The Kähler condition is used. Well, I think already here having a holomorphic coordinates such that the metric is this is exactly in Kähler. But also, these maybe symmetries of curvature that I'm not. But so.
This is on the derivative or
Okay, yeah. JK bar. So I guess here. Yeah. So here I want to take derivatives here with the. I think I made a mistake here. K L bar. So here maybe I wanted to write K L bar. Yeah, thank you. Yeah. So. Okay. So now with this background for the Ricci curvature, we can go back here to the theorem, and we can write down this equation for for the Ricci flat equation, we can write it down. So I'm heading towards what's called the Monge-Ampere equation. So this is the
Sorry, maybe
Yeah.
another stupid question.
Please.
This determinant is real, no? The determinant
That is true. Yeah, the determinant is what is a Hermitian positive definite Hermitian matrix. So the determinant is real. Yes, that's right. Yeah. So actually, so this is in Kähler geometry. This is actually the volume form of local coordinates. In Riemannian, there is a square root. But this is this is exactly also this is the square root if you consider the real determinant of that. But yeah, this is always positive, and this is always positive, and the square is what you obtain if you regard this metric as if instead of doing this, you just do the calculation with real parts, imaginary parts, then here you will get the square root of the dimension. So now I want to write down, we can write down the equation for a metric to be Ricci flat to what's called the Monge-Ampere equation, or complex Monge-Ampere equation, complex Monge-Ampere equation, and it goes as follows. So this assumption C1 of m equals 0. We'll imply that there exists this omega, this n0 form that is holomorphic. So what we want to show is that this omega Kähler, the equation that we want to solve is basically this equation. So in local coordinates, this equation will be like, in local coordinates, this is saying that the determinant of G is just equal to some, the determinant of G is just equal to some mod f squared, where f is some holomorphic function. If you write in local coordinates, because this in local coordinates is just a holomorphic function, the section is just a holomorphic function, and then the volume form is just the determinant of the thing. So then you see from here that now the key thing is that if you have a holomorphic function and you do this thing here and you plug in here a holomorphic function, you get 0. So nowhere vanishing, yeah. Holomorphic nowhere. Holomorphic nowhere vanishing, never 0. And f is never 0. So, but then the basic calculation, if you want, is if you just do set bar set some indices KL, let's just do the same. So let's just do the same here is set K, set bar L of log of the determinant of G. Let's say I said it's a holomorphic function. So that this is a very basic fact, it's a very basic calculation. So log of holomorphic function square, so this is the same as doing. It's okay. Work out, and then this is the same as writing a log of f plus log of f bar, and then this is 0 because so let's do first on this one. This one is 0 because f is holomorphic. Log of f is also holomorphic. When you take the set bar derivative, is 0. And same for the other one. F bar is anti-holomorphic. It's anti-holomorphic. The same for the log. When you take the derivative with respect to set, it vanishes. So this is a 0. So this is the key equation that we want to solve. So this is the equation that we want to solve. We want to solve this. So if you prove existence of this a metric with this volume form, with this prescribed volume form, then you solve the problem. So I want to show existence. And now, what is this? This is a. You can write this as a PDE, but now it's where we use this condition here. So this condition in the homology class. So I want to use this condition that this metric. I'm not finding this metric in the wild. I'm just finding a metric that is in the same homology class. Phi here is a smooth real function. So if I want to find it in the same homology class, the metric will actually be forced to be of this type. So Kähler metrics are always locally given of this form. So you can think that these Kähler metrics always have what's called a Kähler potential, which say that the metric is basically the Hessian of a function, a complex Hessian of this, a complex version of the Hessian of the function. There is a global version for in the compact case. It's called the bar lemma that says that in the same homology class you can parameterize all the Kähler metrics in this form. So this is the. So we want to find phi, this real function, such that the equation is satisfied. So omega is our background metric. We started with some random, some Kähler metric, and then we want to deform that metric by adding this function, the part of the function, in such a way that the volume form of this is this prescribed one. So how do we do this? I'll just say what is the strategy for Yao. First of all, this now becomes a PDE. This is what's called the complex modular pair equation. So it's just a second order nonlinear, fully nonlinear PDE on this function phi. But we're in sort of good shape because I believe this equation is kind of it's called what's called elliptic equation. The linearization of the equation is the Laplace operator. So the method of Yao for solving this equation is what's called the continuity. So the continuity method works as follows. So we want to solve this equation. Well, we have some, let's say, what about the omega? Omega is not going to solve the equation. So omega, I will just write it that omega is not going to solve the equation, but we will start from omega and deform it to the solution. So we start with omega naught. There is no phi, so here these two volume forms will differ by a factor. There's one factor. And then, so f here is some smooth function, given function, some smooth given function. And then what you want is you just want to deform this by, so we want to deform, so this will become now phi t, so phi t will start with just 0, well phi 0, we start with the function 0, so we start at omega naught, and we deform it by solving this equation. So we solve this for t, sorry, I think here I wanted to write 1 minus t maybe, because we start with f, so we start with the non-solution, so we start with f, so we start with 1 minus t for t in 0, 1. And the key thing is that the difficult thing of Yao is proving that this actually you can solve all this family of equations all the way. You start with t equals 0 with the trivial solution, you start with some real given solution, and then you can deform it all the way up to t equals 1. When t equals 1, this is just as 1, and then you have your Ricci flat metric. So that's all I have to say for thanks.
What would have happened? Is there this holomorphic form that is never zero? Is that unique? Is that form unique?
This one is unique up to a constant, yeah.
Okay.
And I didn't mention here, but one needs to be careful with constants because you need to integrate over the manifold and you need to get the same number. So probably there are some constants that there might be some constant also here.
So that the one normalized in some way.
Yeah, that's true. This holomorphic form exists and is unique up to constant, but you need to normalize such that the total volume of this volume form on the manifold is the same as the volume of this omega you start with. So you.
So it is unique for the problem that we want to.
Yeah, that's true. Yeah, it is for yeah. Yeah.
How does this continuity method work? Is it some kind of continuous induction scheme?
So in some sense, so some people say that the Yao proof an undergraduate student can understand because it's all maximum principle. So the thing is, this continuity method is openness is sort of automatic because the linearization is Laplacian. So openness, you can if you have a solution for some t, you can always perturb the t for because the linearization is the Laplacian. But then the key difficult thing is to prove closeness, and those are called the a priori estimates. And it's really an incredible use of maximum principle. It's just and it's a lot of calculations in local coordinates with curvature, different curvature quantities and controlling.
Maximum principles for these monopair conditions.
Is maximum. So I should say there are actually several steps in these a priori estimates. So what needs to bound this what's called this C2 alpha norm of functions, but there are different steps. Sorry, I need to say first. First, there is a bound on the C0 norm of these functions, and that uses Moser iteration. Integration is a Moser iteration for bounding the C0 norm, and then there is the maximum principle. There are some special inequalities one has to consider here that they involve curvature quantities of these metrics, and it's called Cherner and Lou inequalities. There are some special inequalities that apply for this that allows you to bound the C2 norm of a function once you bound the C0 norm. So yeah, I think Yao solved this problem in this compact setting using this maximum principle. I'm not sure what's the story like for in PDEs, like for bounded domains on CN. How is this equation solved? I'm not very. I think some of the same. Yao himself, he extended some of these methods for like bounded domains in CN, but it was first done in the compact case. So.
Correct me if I'm mistaken, but you have defined this omega Calabi-Yau as the one that has each probability equals 0, or?
Yes, and actually the name Calabi-Yau, a Calabi-Yau metric by definition is a Kähler metric with 0 Ricci curvature.
Okay. My question is, do you know the relationship between this Calabi-Yau and why does appear Calabi-Yau in string theory?
No, I just know that there is something called supersymmetry, and there are some supersymmetric models in string theory, and they require something called the parallel spinors. And the thing is that this holomorphic volume form, when you have this Ricci flat metric, this holomorphic volume form is sort of a parallel volume form with respect to the metric, and there is some identification of spinors with forms, differential forms, that gives you the parallel spinor that allows for supersymmetry. So I think for physicists it was interesting as a source of metric with parallel spinors. But yeah, it's out of my reach. Yeah.
More questions? Maybe you mentioned earlier, if the C1, if the first term vanishes, it's almost equivalent to having this holomorphic volume.
Yeah, there is a detail there. But
I'm curious, like, generally you can find it to be smooth, I guess.
that's true. You can always find, yeah.
And how? What is the?
Well, I just didn't want to say. It's just you can always find with this, if the C1 is equal to 0, you can find a smooth volume form, but it's not holomorphic. So it's just a volume form. But when you express it in local coordinates, it's of the type that you want. It's like a holomorphic function. But it's just that this if C1 is equal to 0, it doesn't imply that the line bundle is holomorphically trivial. In general, there might be something called torsion in the C1 might be a torsion class, and then one has to take like covers to get the trivialization. But it's really a problem sort of in topology that is not that. Okay, thank you. And I want to, and since I'm in the last, I just want to thank the organizers, David, Anup, and Mats for having this wonderful event and for all the work that they put into making this possible. So thank you.